The topic for this lecture is definitional equality. First, let's recall primitive recursion, or recursive functions over terms, and how to reduce terms involving recursive functions by beta reduction. So the example is function plus, which takes two natural numbers and computes their sum. So in order to compute their sum, we introduce recursive function p, and then we perform case analysis on the first argument x. If this is phi 0, then we return y, because 0 plus y is just y. If this is x is a successor of z, then we make a recursive call with argument z, and then apply this successor. So what this means is that if x is z plus 1, then in order to compute x plus y, which is z plus 1 plus y, which can be rewritten as 1 plus z plus y. So we first compute the z plus y by calling this recursive function, and then apply the successor to add 1. So that's the idea. So z plus y will be computed by this recursive call p of z. And it turns out that we can show how to reduce terms involving plus. So here's an example. Plus successor 0 t. After two beta reductions, we have recursion p of successor of 0, because this x takes this first argument of p0 y, and y takes the second argument, so this is t. Or if p successor z, then we take successor of p of z. And after another beta reduction, we have, because this successor 0 matches this one, we have to take this branch. So we take this branch, successor of p of z. In this case, z is going to be 0, because we are performing pattern matching between this one and this one. So essentially, we have to find a term that expands p of 0, which is, let's copy the whole term here and change this argument from successor 0 to 0. So it's going to be recursive p of 0 of p0 t and p successor z of successor p of z. So that's the result of applying beta reduction one more time. And finally, if we apply the beta reduction to this inner term, then we have this one matches with the first branch, so we simply take a t. So we show that this plus successor 0t eventually beta reduces to this one. Now, we would like to take advantage of reduction of terms, for example, from this term to this term. in deducing judgment involving predicates. That is, we'd like to consider some judgment using predicate where we know that t reduces to another prime t prime. So the goal is we would like to be able to prove a over t prime true if this is the case. In some sense, we'd like to identify these two terms when we'd like to deduce new judgment, a truth judgment. So here's an example. Previously, we defined this predicate natural number equality. And we know that plus 0, 0 beta reduces to 0. And the question is, can we deduce plus 0, 0 natural number equality 0? So is this true? The answer is actually no at the moment. Because if we go back to the introduction rule for this judgment, then we have only two cases, 0 equals 0 and successor x is equal to successor y if x is equal to y. Because we have these two introduction rules only, there's no way to deduce this judgment, simply because this term plus 0, 0 matches neither the term here, 0, nor this term, successor of something. So in other words, this plus 0, 0 is not 0 or successor of another term. So there's no way to apply these introduction rules to deduce this judgment. So this is not provable. But we'd like to be able to prove this judgment somehow, because our understanding of terms and their reductions tells us that it's okay perhaps to identify this term plus 0, 0 with this simpler term 0, because this beta reduces this simpler term. So we would like to be able to prove this judgment. So to this end, we introduce this notion called definitional equality. So the basic idea is that because these two terms are related to each other by beta reductions, which means that this one beta reduced to this simpler term, we'd like to identify these terms when deducing truth judgment is concerned. In other words, from this beta reduction, we'd like to identify plus 0, 0 with 0 somehow, and then use them interchangeably in this judgment. Then perhaps the problem of proving this judgment reduced to proving the judgment 0 natural number equality 0 true, because this one and this one, these two terms are definitionally equal. So that's the basic plan. So let's develop this notion of definitional equality. The basic idea is we introduce new form of equality. Say this is definitional equality, and two terms are definitionally equal if they both reduce to the same term by beta reductions. That is, if term t beta reduces to another term r, and s also beta reduces to the same term r, then we say that these two terms are definitionally equal. So let's suppose that these two terms t and s are definitionally equal. That is, we have this diagram showing that t beta reduces to r and s beta reduces to the same term r. Now, whenever we have a proof of a t true, then we'd like it to allow a of s true. So here's an example. So we can show that plus 0, 0 is definitionally equal to 0 because plus 0, 0 beta reduces to 0, and 0 also beta reduces to itself after 0 beta reduction. So we have this equality. Then perhaps plus 0, 0 natural number equality 0 is also provable because we have this judgment. This is provable by applying the introduction rule. But we have shown here that these two terms are definitionally equal. So it's okay to expand this one into this one. So this judgment is not provable directly from the introduction rules for this natural number equality, but it can be shown provable with this indirect proof. So first, we prove this judgment, and then we apply definitional equality and replace this one with this one. In this way, we can prove this judgment. So that's a basic idea. So before presenting the formal definition of definitional equality, let's inspect its property. So this is one example of definitional equality. And this example shows that definitional equality extends syntactic equality. So we have this notion of a syntactic equality. For example, x equals x. This is syntactically equal. So if we interpret this symbol, this equality symbol, as a syntactic equality, this is a valid judgment. Intuitively, the left-hand side and the right-hand side are syntactically equal. So it is syntactically equal. But these two terms are definitionally equal as well, because the left term x beta reduced to the right term after 0 beta reduction. So this one is okay under syntactic equality and also under definitional equality. But what about this one? Plus 0, 0 equals 0. First of all, it's not syntactically equal. Literally, the left-hand side is not syntactically equal to the right-hand side. By syntax, these two terms are different, so they are not syntactically equal. But we have shown that these two terms are equal under definitional equality. So these two examples show that definitional equality strictly extends syntactic equality, which means that if the two terms are syntactically equal, we automatically have definitional equality as well, but not the other way around. The point I am trying to make here is the notion of equality depends on the context. The interpretation of this symbol, this equality symbol, is subject to the definition. It's a definition. For example, we may assume syntactic equality, or we may assume definitional equality, and there are several other notions of equality. So keep in mind that from this point on, this symbol assumes definitional equality. And furthermore, this symbol for definition equality has nothing to do with this symbol for natural number. This is just a special predicate. So originally we decided to use, for example, something like EQ, M, and N. But as a syntactic convenience, we decided to replace this predicate with this infix operator. So that's all. This has nothing to do with the notion of equality, as in syntactic equality or definitional equality, but it is just a predicate that we have defined with the two introduction rules. Now, let's assume definitional equality for this symbol. Until now, we always assume the syntactic equality for this symbol, but now it's going to be definitional equality. So let's formally define this definitional equality. So we have new judgment T equals S. This is new judgment. And for simplicity, we don't write T equals S true, because it is implied that this is just valid judgment, so we don't write it true here. And the introduction rule for this definitional equality is, previously we stated that two terms are definitionally equal if they both reduce to the same term. So there exists some term R such that T beta reduces to R, and also S beta reduces to R. So this is the definitional equality introduction rule. But an important assumption here is, in this rule is, this beta reduction can be applied to any subterm. So for example, we know that plus 0, 0, beta reduced to 0. So therefore, this is also valid beta reduction. Because this inner term can be reduced to this one. And the assumption here is this beta reduction can be applied to any subterm. So this one beta reduced to this one. So therefore, the whole term also beta reduced to success over 0. So in this rule, you want to remember that beta reduction can be applied to any subterm. So according to this definition, this definitional equality introduction rule, we obtain a special case. So it's a special case if term T beta reduces to S, then term T is equal to S. Or S beta reduces to t, then we have this definitional equality. For example, in the second case, let's say S beta reduces to t, but we know that t also beta reduces to itself. So therefore, we have just found a common term that both terms beta reduce to. So therefore, we can show that S equals t. And if we change the position of these two judgments, then we would have t equals S. So this is a special case. If one term beta reduced to another term, then these two terms are definitionally equal. So this is the introduction rule. And in order to exploit an existing judgment of this form, definitional equality, there should be an elimination rule. So let's develop an elimination rule. And the original motivation for introducing definitional equality was if these two terms are definitionally equal, but we have already found a proof of, for example, A of t true, then we'd like to be able to deduce A of S true as well. So that was the whole motivation for developing definitional equality. So let's turn our informal understanding of this idea into a concrete elimination rule. So this is the introduction rule. And the elimination rule, so definitional equality elimination rule. So it is about how to exploit an existing judgment involving definitional equality. And the idea was, if we have A over t true, then we decided to permit this judgment. So that was the idea behind the definitional equality. So what this elimination rule implies is that once we establish the equality between these two terms, we stop to distinguish between these two terms when we deduce these truth judgments. We can, in other words, we can just use these two terms interchangeably. And the transition is silent here. And this becomes clear once we reformulate this rule in terms of proof terms. So suppose that we have a proof term M of type A of t. So here we interpret the A of t as a proposition, but here we interpret the A of t as type. And we know that t is definitionally equal to S. Then this elimination rule allows us to silently change the type of a proof term M from A of t to A of S. So if this was a programming, this was a program written in programming language, then this inference rule, this typing rule, changes the type of this program silently. So the proof term, this proof term does not change at all. It stays the same, but its type silently changes. So this is the elimination rule for definitional equality, and this is the introduction rule for definitional equality. Now let's investigate the properties of definitional equality. This is the definition of equality. First, definitional equality is reflexive, which means that every term is definitionally equal to itself. And this is pretty easy to see because term t beta reduces to itself after zero beta reduction. And what about commutative? It turns out that this definitional equality is commutative, which means that if t is equal to s, then we can change their positions. So s is equal to t. Notice that this is not built into the definition of, the introduction rule of the definitional equality. It is a derived property. So we have to show that this is indeed the case, and it's pretty easy to see. So according to the introduction rule written here, this equality means that there exists some term R such that both T and S reduced to. So therefore we deduce T is equal to S. Now it's just a matter of changing the position of these two judgments. So we make copy over here. So S beta reduces to R and T beta reduces to R. So according to definitional equality introduction rule, we can show that S is equal to T. So this shows that definitional equality is commutative. And perhaps to your surprise, definitional equality is not transitive. So if it was transitive, we would have T is equal to S and S equal to R would imply T equals to R. So that's the notion of transitivity. But it turns out that this is not the case. To see why, from the definitional equality between T and S, we know that there exists some term that both T and S beta reduces to. And from the definitional equality between S and R, we know that there is another term such that S beta reduces to this term and R beta reduces to this term. If these two terms happen to be the same term, then we would have this definitional equality between T and R, but there's no guarantee that these two terms are identical. Or if these two terms are different, there's no guarantee that both terms would reduce to another one. So the existence of this term is not guaranteed. So therefore, we cannot claim that term T and term R are definitionally equal. Their definitional equality would require the existence of such term. But from these two, from this diagram, we cannot guarantee the existence of such a term. So it turns out that this definitional equality is not transitive in general. However, definitional equality is weakly transitive in this sense. If T is equal to S and S is equal to R, then A of T true implies A of R true. And this is easy to see from the definition, from the elimination rule of definitional equality. So here's the elimination rule for definition equality. So whenever you have definition equality, you can replace this term T with this term S. So now you have A of T true, and from this definition of equality, it's okay to deduce A of S true. And from this definitional equality, it's okay to deduce A of R true. So as far as deducing truth judgment is concerned, we may assume that definitional equality is effectively transitive. But definitional equality is not transitive, strictly speaking. It's only weakly transitive in this sense. Let's see some examples of definitional equality. So examples of definitional equality. First, plus 0x is equal to x is definitionally equal. It's just a matter of reducing this term to this one. So in other words, this term eventually beta reduced to x. Because of this one, because of this definitional equality, now we can deduce this one is actually natural number equal to x. And this one is different from this one. This is the definitional equality. And this one is the predicate, another name for this EQ. And what about this one? Plus x0 equals x. And it turns out that this is not the case, because if you try to reduce this term, you immediately get stuck because you don't know the concrete term for this variable x. So the reduction of this term gets stuck. So you can never find a term, a common term, such that these two terms are reduced to. So this is not actually definitionally equal. And in order to show this one, so for example, if you'd like to show for every natural number x plus x0 definitionally equal to x itself, you have to actually use induction on term x. And in the previous lecture, we learned the technique. Finally, plus successor xy. This is actually equal to successor of plus xy. And it's pretty easy to see. So after two beta reductions, we have recursive p of successor x of p0 y, or this is p successor z, and this is a successor of p z. And this successor x matches with this one. So we take this branch. So it reduces to successor of p of x. And this is precisely, this one precisely reduces to, this term eventually calculates plus x plus y. So therefore, this one beta reduces to this one, and we have this definitional equality.